All right, let's get started. Well, good evening. Welcome, everybody. I'm Professor Sean Tavalia, founding member of the board of Hamptons Observatory and academic chair for physical sciences at Suffolk County Community College. On behalf of my fellow board members and colleagues at Suffolk County Community College, I'd like to welcome everyone to tonight's presentation. For those of you who are new or are unfamiliar with our organization, Hamptons Observatory was founded almost 20 years ago. It's kind of odd to say that at this point, with a mission to provide free, year-round, family-friendly educational events that focus on the sciences and the natural world. After tonight's presentation, please visit Hamptons Observatory website to learn about our future presentations, to join our email list, or donate to help ensure that we can continue providing these incredible opportunities. If you feel inspired by tonight's presentation, this will be a little shameless plug, please visit Suffolk County Community College, where you can begin your journey into a scientific career at one of our 3 campuses in Brentwood, Selden, or Riverhead, New York. Or if you're one of the out-of-state participants tonight, from the comfort of your own home in our online offerings. As we begin tonight's presentation, I ask that you keep your microphones muted, and please feel free to post questions in the chat. At the conclusion of the presentation, we'll do our best to answer all of your questions. And then one little reminder, or if you haven't aware of this, at the bottom of your Zoom screen, there'll be a spot where you might see a little smiley face with a plus sign that says reactions. If you're asked to raise your hand throughout the presentation, click there and you'll have a little emoji that can raise your hand, give the icon so that the presenter can see who's raising and who's not, if you're asked. So tonight's speaker is an astrophysicist and science communicator who spends her time learning about the universe and sharing its wonders with everyone around her. After graduating from MIT, she completed her PhD at the University of Michigan, where she worked on weighing clusters of galaxies and figuring out what the cosmos is made of. She's now at the Harvard Smithsonian Center for Astrophysics, spreading the joys of space through NASA's universe of learning and continuing her research into the composition of the universe. When she's not staring at the sky, both with the naked eye and through the data from giant telescopes, she enjoys reading, crafting crazy desserts, which I would love to hear about, and taking an inordinate number of nature photos and writing poetry about the cosmos. So with that, please join me in welcoming Dr. Rutuparna Das. Ruta, take it away. And don't forget to unmute.
Yes, thank you. Thank you very much, Sean. Hi, everyone. Thanks, Sean and Donna, for having me here. I'm excited to talk to you today. And without further ado, let's get started. So I will share my screen. And ideally, this will go as it did when we were testing. All good? All right. Okay. So a long, long time ago, in galaxies far, far away, light was emitted. This light has traveled millions to billions of light years, curving around the twists and turns of space to fall through our atmosphere and land on our telescopes. So today, I'm going to talk to you about how we can use these twists and turns of light to learn about the dark side of our universe. So, quick question, and you can use that little reactions raising hand to respond. How many of you have heard of the Big Bang? Quick show of hands. And yeah, as expected, you know, that's most of you. I'm seeing thumbs ups and raised hands. You can also feel free to put things in the chat if you can't. Yeah, I have some raised hands in the chat. Yes. So the Big Bang, right? The universe expanded, got really, really big, really, really quickly, continues to expand to this day. And how do we know this? We know this because we found about a century ago that galaxies are moving further away from us. And upon further study, we found that galaxies all around us are moving further and further away from us. This work was, one of the key people doing this work was Edwin Hubble, whose name you may have heard, who the Hubble Space Telescope is named after. And yeah, from this, we realized that, okay, galaxies are all moving further and further away, which means they must have started somewhere, which is where we got the Big Bang. And since then, we have had a bunch of other data show us that the Big Bang is indeed what we believe started our universe. So, okay, Big Bang, universe is expanding, continues to expand. Now, I hope all the hands have come down. Raise your hand somewhere in any of these sessions if you have heard of the Big Crunch. I will give people a few seconds. And interesting, this is an interesting group. I'm getting more hands up than I usually get for the Big Crunch, which is great. But as expected, fewer than we got for the Big Bang, which I'm going to say is a good thing, and we'll see why. So, okay, everybody can put their hands down. Excuse me. So, what is the Big Crunch? Well, the universe, as I said, we found that galaxies were moving further away from us. We found that the universe was expanding, and we thought, well, it's got to stop at some point. Why does it have to stop? Because of gravity. There's gravity everywhere. Every object in the universe has gravity, right? The same gravity that if I take, this is like a, I don't know, star squishy toy. If I take this and throw it up, the same gravity that brings it back to me is the same gravity that pulls us to the Earth, pulls the Earth to the sun to the center of our Milky Way, and pulls every object in the universe to every other object. So if every object is pulling at every other object, we figure, okay, galaxies are getting further and further away. This is just residual stuff left over from the Big Bang. At some point, they've got to slow down because gravity's pulling everything together. It's all got to slow down and then start collapsing in on itself, and everything should come together eventually in a big crunch. This is the theory of the universe that I remember reading in like a giant kids board book in the 1990s. And the 1990s is when we were trying to figure out when this will happen. You know, when is the universe going to collapse? When is the universe going to end? If you'll permit me some drama. When will the universe end? And we wanted to know, you know, how long do we have? How long do we have before the galaxies stop receding, before the universe stops expanding and starts contracting? Do we have billions of years? Do we have trillions of years? Is it next Tuesday? You know, how long do we have before the universe ends? And to do this, there are many ways of studying this. One of the ways, and the way people were doing this in the 1990s, was using type 1a supernovae. Oh, I forgot my house slide. Yes, how do we study this? How do we figure out how the universe is slowing down? One of the ways is to use type 1a supernovae. Now, supernovae are stars that have exploded, or stars that are exploding. There are many types of supernovae. One you may have heard of is when a giant star ends its life and collapses in on itself and explodes. That's called a type 2 supernova. That's not what we care about today. There's this other type of supernova called type 1a, which happens when we have stellar remnants called white dwarfs. We have small stars that have ended their lives. By small, low mass stars, I'm talking about stars like our sun. Our sun is a relatively low mass star. So we have relatively low mass stars like our sun that have ended their lives and have turned into white dwarfs. They're called that. They're basically giant balls of carbon under a lot of heat and pressure. Now, there's something that determines whether a star is going to turn into a white dwarf or whether it's going to explode in a supernova and turn into something else. And that something is its mass. There is a limit of mass, 1.4 times the mass of our sun. This is called the Chandrasekhar limit, which was found by the scientist Subramaniam Chandrasekhar. He did the math on this, figured out whether a star would explode or not. And the thing is, when it comes down to its white dwarf state, if that thing is less than 1.4 times the mass of our sun, that star is going to rest. It's going to stay a white dwarf. But if it's got more mass than that, it will continue collapsing. It will continue with other processes until we have a supernova explosion. Now, that's all great for stars that are individual stars merely living their own lives. But some stars are in binary systems. There are two stars orbiting each other. And this picture you see here is an artist's impression, not a real picture, of a binary star in which we have one white dwarf, which is in the middle of this disk of stuff, and one regular star, one main sequence star. And what the white dwarf does sometimes is it starts pulling mass off of the other star. It starts pulling mass off of its companion and growing. This is all good and fine, except at the point in which that white dwarf reaches 1.4 times the mass of our sun, it explodes. And that is called a type 1a supernova. Why did I tell you this whole background of type 1a supernovae? Because I wanted to show that every type 1a supernova starts in a similar way. It is something smaller than 1.4 times the mass of our sun, growing until it reaches that limit. And that's very important because this means that every type 1a supernova starts from the same thing, starts from an object of the same mass, which means every type 1a supernova gives off the same amount of energy. So these are a few type 1a supernova remnants, what are left over after a few of these types of explosions. And you can see they're sort of similar, they're all kind of spherical. They're all, I should have put some non-type 1a supernova remnants here. You would see they're all over the place. They're not all spherical like this. I didn't think of this sooner. I should have put something for comparison. But this is to show that their energy levels are all similar. From this, we use them as something called a standard candle. Basically, anywhere in the universe a type 1a supernova goes off, we know how bright it is. Whether it's somewhere right in our cosmic backyard or if it's, billions of light years away, if a type 1a supernova goes off, we know how bright it's supposed to be. So think about if you have a bunch of candles, right? And if they're all the same type of candles, just one flame, they all have the same brightness. If a candle is closer to you, it's going to look brighter to you. If it's further away, it's going to look dimmer. And using that, using how bright it looks to us, we can figure out how far away it is, right? So if a supernova, type 1a supernova looks really bright, we can say, oh, that's probably close to us. If a type 1a supernova looks really, really dim, we can say, oh, okay, that's probably really far away because we know it's actually really bright. Yes? So that was a little detour for supernovae that we took. And now we are wondering, what does this have to do with the expansion of the universe? So the expansion of the universe is causing things to move further and further away. It also affects the brightness of a type 1a supernova. Or rather, it doesn't affect the intrinsic brightness, but it affects the brightness of the light that comes from the supernova and reaches us. So by looking at a lot of type 1a supernovae, where we know the actual brightness of all of them. We know how bright they are. We also can use other factors of the explosion to figure out how far it actually is. So we know how far it is, and we know how bright it actually is, so we can calculate how bright it should look to us. That's the key point. We can calculate the expected brightness that we think we're going to see without dark matter doing without the expansion of the universe doing any of its meddling. But the expansion of the universe is doing its meddling, and so the brightness is different. So by comparing these expected brightnesses to how bright we actually see these supernovae to be, we can calculate the expansion of the universe. I don't want to get into like more technical detail than that. But basically, yeah, so it's this comparison. This is how bright we think it should look. This is how bright it looks. The difference is caused by the expansion of the universe. And this science was done by several different groups, particularly in the late 1990s. Two completely separate groups of researchers were studying supernova, type 1a supernovae, to try to figure out how the universe was expanding and, to try to figure out how quickly it was slowing down, as we thought, right? And it's great that we had two groups doing this independently, because if two groups are solving a problem separate from each other, if they get the same result, then we have more confidence in the result, right? The two groups can't have the same experimental errors, or they can, but it's far less likely. So, late 1990s, these two groups found, to their astonishment, that the universe was not slowing down at all. It was, in fact, accelerating. The universe was getting bigger and bigger. Is getting bigger and bigger, faster and faster. This was incredible. This was absolutely stunning. The entire astronomy community, I want to say much of the wider physics and scientific community, was in shock, because this made no sense whatsoever. This was like if I took this thing and I threw it up, and instead of coming back to my hands, it got faster and faster and flew off into space. That made no sense, because gravity exists. Gravity is a thing. We can feel it. We can see its effects. So how could the universe not only not be slowing down, how can it be getting faster? Well, we're scientists. We spent some time in our shock, and then we brushed off our shoulders, got up and said, okay, where did we go wrong? What are we missing in our hypothesis? What are we missing in our understanding of the universe? Because clearly it's something wrong with our understanding. The universe is never wrong. The universe, it is what it is. It's showing us what it is. And, assuming our data and our calculations are correct, and, we've double and triple checked them. As I said, we have the two groups doing looking at the same thing. So we have double confidence from there. The universe is never wrong. So it's us. We have to figure out where we went wrong in our understanding. And we thought, okay, clearly there is some form of energy that is causing the universe to get bigger and bigger, faster and faster. That's causing the universe to expand, to accelerate. We say it's some form of energy because to counteract gravity, it's got to be providing some energy. We know that. And we know that we can't see it. We haven't seen any inkling of this anywhere. So in all of our wisdom, we name it dark energy. And I say in all of our wisdom because astronomers are hilarious when it comes to naming things. Slight detour here. As I said, we couldn't see it, so it was dark. We knew it was energy, so it's called dark energy. we built a very large telescope, and it is named the Very Large Telescope, a VLT for short. You can go look it up. We built a bigger telescope. Another group built a bigger telescope and called it the Extremely Large Telescope, or ELT. Currently, there are actual plans for the building of the Overwhelmingly Large Telescope. But I'm going off on a tangent. But yes, I'm just saying it's fun when you try to name things. So we named this dark energy. Dark energy is the name given to whatever is causing the universe to expand faster and faster. Whatever is making the universe accelerate, we're calling it dark energy. And all right, great. Now we want to find out more about dark energy, right? We want to learn about how much of it there is. We want to know what it is, but I'm not going to go into that today. That's a far more theoretical issue, and we don't know is the answer at the moment. There are possibilities, but we want to know how much of it there is. Why? Because we're trying to figure out what happens to our universe. How's our universe going to end? Is it going to end? What's going to happen to it? And so if there isn't a lot of dark energy, if gravity overpowers dark energy, then at some point, this expansion will start to slow down, it will stop, and it will contract and end in the big crunch. That's if there isn't that much dark energy. Now, if we have a lot of dark energy, if dark energy overpowers gravity, then the universe is going to continue to expand and continue to accelerate, and everything's just going to fly apart. That's called the Big Rip, by the way, for those of you keeping track of your big ends of the universe, fates of the universe. Or there is the option of dark energy and gravity sort of balancing each other out. If that happens, the universe will continue to expand because there's nothing to stop it from expanding, and object in motion will continue to be in motion unless there's a force stopping it, right? So if gravity and dark energy balance each other out at some point, the universe will just continue to expand, but not accelerate or slow down. And I believe some scientists call this the big freeze, because the universe will just get very big and there won't be enough energy to go around and everything will be cold. But anyways, so we want to know how much dark energy there is to figure out what's going to happen to our universe. Now, there are several ways of studying dark energy. It's kind of complicated. This is easier said than done because, as I said, we can't see it. We don't know anything about it. How do we study it? One of the ways is using those type 1a supernovae that we talked about before. Another way is using, excuse me. Another way is using clusters of galaxies. And we're going to talk more about that right now. A cluster of galaxies is exactly what it sounds like. It's a bunch of galaxies that are bound together, they're orbiting each other. That's a cluster. Clusters of galaxies are the most massive gravitationally bound objects in the universe. What this means is they're pretty much the biggest things we have in the universe that we can count. Like, oh, here's a cluster, there's a cluster, there's a cluster. Gravity's pulling them together. If we get any bigger than the cluster, we've just reached the cosmic web in the universe as a whole. So these clusters are so massive, excuse me. Sorry, I have a bit of a cough. These clusters are so massive. They have so much mass that they have really strong gravity. Mass brings gravity. So these clusters have extremely strong gravity. So strong that as things pass by, they fall in. Other galaxies are passing by, a cluster gets close to other galaxies, those galaxies fall in. They add to the cluster. Galaxy clusters grow over time. But dark energy is causing everything to move further away from each other. So because of dark energy, a lesser amount of stuff actually gets close enough to the cluster to fall in than there would be otherwise. Dark energy is hindering the growth of galaxy clusters, which means if we can study how a galaxy cluster grows over time, we can study dark energy. It's sort of a tug of war between gravity and dark energy. Gravity pulls things in, dark energy causes things to move further away. So if we can quantify how galaxy clusters grow over time, we can ask the question, hey, how much dark energy does there have to be for the clusters to grow at the rate that they do? It's this balancing act, and if we know the gravity half and we know what's happening to the clusters, we can figure out the dark energy half. So that's great. Now we need to figure out how clusters grow over time, and for that, we need to figure out how to find the mass of a galaxy cluster, which is, again, easier said than done. And here I have weighed this galaxy cluster against suns because we usually refer to things in terms of the mass of the sun, except in the case of galaxy clusters, we get to 10 to the power 12 or 13 or 14 times the mass of the sun. So yes, how do we find the mass of a galaxy cluster? That's a fun question. Okay. Perhaps we can just count the galaxies. Every sort of smudge you see in this image is a galaxy. So what if we count the galaxies? We know general, average mass of galaxies. Maybe we can get an understanding of how much mass there is in the cluster. That's great, but unfortunately, the galaxies, the things that we can see here, make up only 1% of the mass of this galaxy cluster. These galaxies comprise 1 part in 100 of the whole mass of this cluster. So then we think, okay, how can we see more of this cluster? How can we understand more of this cluster? Well, this is an image from the Hubble Space Telescope. It is looking at this cluster in visible light that our eyes can see. But we've got lots of other types of light, and wow, this image is coming up really blurry for some reason. So please excuse the very pixelated words on here. But, we have many different kinds of light, like radio waves or X-rays or gamma rays or infrared. These things show us things we can't see with visible light, and they show us different parts of an object. For example, here's our sun. Here is the surface of our sun in visible or optical light that our eyes can see. And it looks kind of boring. I mean, it looks like there's not much going on the surface of our sun. There are a few sunspots, but not much else. Side note, by the way, right now, the sun has a sunspot on it that is visible to our eyes without a telescope. You need eclipse glasses, but if you have eclipse glasses, you can go out tomorrow and through the eclipse glasses, look at the sun and you will see a sunspot on it. It's really cool. Just a side note. I got very excited about this today. But yes, in light that our eyes can see, the sun looks kind of boring. However, we can use, say, infrared light, which is the heat signatures of things. So if you've ever used night vision goggles or watched somebody on TV use night vision goggles, they're using infrared light. So the sun in infrared is more interesting. It's not as uniform. We have some jaggedy things here. We have bigger sunspots. Okay. Then we use ultraviolet light. And the sun actually has a lot of activity going on it. There are these solar storms going on. Magnetic field lines are twisting and turning all over the place. Gas and dust is following these magnetic field lines. We use X-rays, we can see solar flares, we can see solar storms. The sun is a very active place. Oh, by the way, just a shout out, this X-ray image is from the Chandra X-ray Observatory, which is turning 25 this year. So happy birthday, Chandra, which is, by the way, named after the same scientist we talked about who figured out whether a star would explode or not. Anyways, so the sun is a very active place, but we need different kinds of light to see all parts of it and to see all facets of the sun. So in the same way, we thought, what if we use different kinds of light to look at a galaxy cluster? What if we, maybe using a different kind of light will show us something more than 1% of its weight, of 1% of its mass. So we use X-rays because a galaxy cluster, all the galaxies are surrounded by this super hot gas called the intracluster medium, and super hot things usually glow in X-ray light. So we see this. It's like this blob that surrounds the galaxy clusters. Okay, so now we can see the blob of gas. That's the intracluster medium. And given the strength of the X-rays, and actually, given the strength of the X-rays, we can figure out how much gas there is, and we can find its mass. So we're like, okay, great, we have the mass. Except, turns out that this intracluster medium is only 10% of the mass of a galaxy cluster. We're still only a 10th of the way there. The rest of the mass of this thing is dark matter. Called that because it does not interact with any kind of light. It doesn't, so you can't see it in visible light, you can't see it in X-rays or radio waves or any other kind of light. We know it's there because of gravity, but it's dark, we can't see it. So we have 1% using the galaxies themselves, 10% of the mass in the intracluster medium, the gas, but 90% of the mass is still missing. So how do we weigh a galaxy cluster? We are back to the question of how do we measure something we can't see? We can't see dark matter using any sort of light. So how do we measure it? And as with our previous questions of that nature, we look at how it affects the things around it. We look at, particularly, gravity. It is matter, meaning it has gravity. That is the one thing we know about dark matter. We know it doesn't interact with light, and we know that it has gravity. So if we look at how its gravity affects everything around it, that can tell us how much dark matter there is, which can tell us the mass of a galaxy cluster, which is what we're trying to find out. So, okay, we will get to this in a moment. There are ways of trying to find the mass of a galaxy cluster. We thought, what if, it's difficult to look at dark matter. Can we use indirect methods? Can we use proxies? Yes, we can. There are certain things about galaxy clusters that we can measure more easily. And if we can figure out how that correlates to the total mass of the cluster, we can use those. One of those happens to be actually counting the number of galaxies. And the number of galaxies does correlate with the cluster mass. So you can get an idea from that. Another way is looking at those X-rays, the temperature of that hot gas, which we can find out using the X-rays, and how bright that gas is. Both of those correlate to how much mass there is in a cluster. And we can also see how light from the edges of the universe, from the cosmic microwave background, as light from the edges of the universe passes through a cluster on its way to us, it gets sort of agitated. It gets distorted. And if we can figure out how much that agitation is, that also scales. The more mass in the cluster, the more the light gets agitated. So great, okay, there are all these indirect proxies which are easier to see, but to figure out the correlation between these and the masses of clusters, we still need to have like a test set where we know the actual mass. The idea is we'll have a test set of a few galaxy clusters, like by few, I mean like a few hundred, but you have a test set of some number of galaxy clusters. And for that test set, you know what these correlations are. And then you can apply that to like all other galaxy clusters. But to create that test set, you do need some direct ways of measuring the cluster's mass. You do need to actually know what the mass is for the members of that set to actually get your correlation. So how do we directly measure dark matter? I mentioned this before. All we really know about dark matter is that it is matter and has gravity. So let's see how its gravity affects the things around it. One of those ways, again, is using the individual galaxies themselves. This time, we're not counting them. Remember, I mentioned that a galaxy cluster is a bunch of galaxies bound to each other, orbiting each other. They're all going around in their own orbits. And the way, just from Newtonian mechanics, we know that the more gravity something has, the faster things are going to orbit around it. So the more mass the cluster has, the faster these galaxies are going to be orbiting. So by taking measurements of how quickly galaxies are orbiting around the cluster, we can try to find the cluster mass. This works if the cluster is a nice, neat, almost spherical or very homogeneous type of thing. But if you have, say, two clusters merging or, other issues, you can't always easily figure out how the orbits correlate to the mass. But this is one direct way. Another way is using that X-ray gas, but using gas science, fluid dynamics, PV equals nRT, which many of you may remember from high school chemistry. A gas has pressure. A hot gas wants to expand. And using the X-ray data, we can tell what the pressure of this intracluster medium, this superhot cluster gas, is. Assuming that a cluster is in equilibrium, that gas is pushing outwards and its gravity is pulling inwards. So we can balance the gas pressure outwards with how much gravity there has to be to pull things in to keep the cluster in place. That's one way. That's another way of finding the cluster's mass. But this assumes that the cluster is in equilibrium, which not all clusters are. Some clusters have weird things going on inside them because of supermassive black holes. In any of these galaxies that you see, if they have jets like spewing out of them, that can mess up these calculations. So we go to a third method of direct measurement, which is what I'm going to talk a little more about right now. This is called weak gravitational lensing. Gravitational lensing means the bending of light by gravity. Gravity pulls everything, even light. You may have, many of you have probably heard of black holes and how light can't escape them because their gravity is so strong. For that to happen, for a black hole to be able to suck in light and for light to not be able to escape, a thing has to be very dense. Galaxy clusters aren't that dense. Light can escape, clearly, because we can see the galaxy cluster. If light couldn't escape, we wouldn't be able to see anything. So light can escape, but as light passes by a galaxy cluster, it gets distorted. It gets bent. And the more mass a cluster has, the more this bending happens. So I'll show you what I mean by the bending of light. Here you see all of these arcs. These arcs are actually strong gravitational lensing. They're basically a stronger version of this effect that you can see with the naked eye, that you can see with the eye when we take these beautiful pictures of space. What we are talking about, by the way, strong lensing is a little rarer. You don't find it as frequently. Weak lensing is far more common and is what we use. So what happens is you have these galaxies in the background. They are not the cluster galaxies. This is a cluster. You have the galaxies far off in the background. As light from these galaxies comes by the cluster, it gets bent on its way to our detector, which is on this end. I'm hoping you all can see my mouse, and if you can't, then somebody should let me know. But yeah, as this light reaches us, it gets bent. So we see these galaxies' shapes to be distorted just a little bit from what they originally were. However, we don't know what the original shape of the galaxy is. How do we know what the distortion is? Like we don't have anything to compare it to because we can only see the distorted version. So what we do is we use the law of large numbers. We use statistics. We say that, okay, galaxies are generally randomly oriented in the sky. They're elliptical, but their ellipses point every which way. However, lensing works in a way that if you have a galaxy cluster in front of it, then the light from these galaxies tends to sort of start arranging itself tangentially around. You can see it seems like they're forming rings around the cluster. This, by the way, is a highly magnified version of the effect. It doesn't, it's not this strong. You can't see it with your eyes, but I did this just to show you guys, just to show you all what the effect is. So we can statistically see how well background galaxies are sort of lining up in a circle around the cluster. The greater this effect, the stronger the cluster's gravity, which means we have a direct measure of how massive a cluster of galaxies might be. So this, by the way, is that galaxy cluster I've been showing you so far. The blue around it is a map of the dark matter that has been created using weak lensing, using gravitational lensing. Where you see brighter blue is where there's more dark matter, but you can see for the most part, it's just a giant blob around this galaxy cluster. And we put it together with the X-rays. You can see, so you have the galaxies themselves, you have the intracluster medium, the superhot gas, and surrounding all of it in this giant blob is dark matter, which we now have a way to see, quote unquote. And I wanted to show you something really cool. I think I do have a minute. Okay, this is a fairly normal galaxy cluster. It's not quite spherical, but still pretty blobby. You don't see much structure. Not all galaxy clusters are that way, and this complicates our observations. This is the bullet cluster, which was one of our first observations of something that showed us like, oh, hey, dark matter is a thing, dark matter exists. The red is X-rays as before. This is two galaxy clusters that smashed into each other. And the X-ray, the intracluster medium sort of tried to pass, like intracluster medium of both galaxy clusters interacted and created this bullet shape in their gas. But the dark energy didn't interact with anything. It just moved. So you have these two blobs of dark energy, they moved past. You don't see much interaction in the blue. And just for fun, I will show you, we try to display our data in many different formats so that people with different learning styles and learning abilities can experience the joys of space. So we have taken this image of the bullet cluster and turned it into music, turned it into sound. There are three different pitches. The galaxies have the set of higher frequencies. The X-ray has the mid-range of frequencies, and the dark energy has the low range of frequencies. As something is higher on the page, it has a higher frequency. And if something is brighter, it is louder. So let's take a minute and listen to the bullet cluster. that was fairly clear. And if you couldn't hear it very well, I can put a link in the chat to Chandra's Universe of Sound, where we have sonifications of a bunch of different space objects. But yeah, you can see that, you know, this is not a regular cluster. But yeah, what we use more regular clusters to do our science, but things like the bullet cluster sort of get in our way. Anyways, so we use gravitational lensing, the twists and turns of light through space, to figure out the mass of galaxy clusters, which we then use to figure out how clusters grow and balance the tug of war between gravity and dark energy to figure out how much dark energy there is, and ultimately use that to figure out what the fate of the universe will be. And I did not leave very much time to talk about the fate of the universe, simply because we don't know yet. We're still doing this research. It looks like gravity and dark energy are probably balancing each other out pretty well. But we are still doing research on this. We don't have a precise answer just yet. So with that, thank you. And I will take any questions.
So the good news, Ruta, is none of us will know. So you could have made up anything you wanted.
I like to share what we know to be true so far. So far we think they'll balance out. But hey, I don't know if there are any high schoolers or early career folks here who are thinking of maybe going into astrophysics. Yeah, you might be one of the people who figure this out.
So there was one part in the chat where Julia wants to know if you could talk about galaxy rivers.
I think you might be talking about the Milky Way rivers. They found a bunch of structures around the Milky Way. I'm not actually very familiar with this. But there is, I think they found some structure around the Milky Way that, honestly, I just know they exist. I am not at all familiar with these. But if you look up Milky Way rivers, I think you should be able to find more information.
So the other two questions are kind of related. Sherry wants to know if you could talk about the distribution of dark matter through the universe. And then kind of related, Dan would like to know if the universe expands at a uniform rate.
Okay. So the distribution of dark matter in the universe is what we call the cosmic web. Actually, you know what? Let me stop sharing this and I can share an image. Because that's going to be way easier than trying to explain what the cosmic web is without showing it. It's basically, it looks like, you know what? No, let me pull this up. While we don't have images of the full cosmic web, we have a lot of simulations that show what it is, and we have seen we have measured parts of it, so it's not like this is all simulations, but I will show you an image from a simulation because that's yeah, that's more complete. Let's see, share screen. Okay, so this is from a simulation where they put a bunch of particles into, when I say a bunch, like billions of particles into a box, basically turned on gravity and said, go forth and show us what the universe would do. And in some cases, you know, they entered dark energy into it. They entered all the things we know about the universe and the laws of physics that we know, and looked at what turned out. And basically, you see that gravity pulls things together on a wider scale. So this is a cluster of galaxies. This is a really large cluster of galaxies. Every like little bright dot you see is a galaxy. So anywhere you see a bunch of them is a cluster of galaxies. But beyond that, we have dark matter filaments stretching across space. These have been observed. People have, like, again, using things like gravitational lensing, have found filamentary structure as well. So the whole universe is basically I mean, when you zoom out, it looks pretty homogeneous. It looks pretty much like the same everywhere, but there is this sort of filamentary structure going through everything. And what was the second question?
So it was the distribution of dark matter, and does the universe expand at a uniform rate?
I'm not sure. What do we mean uniform rate over time? Because that's what we're trying to find out. How is it expanding? And we are finding that it's getting faster and faster. So it's not uniform over time. If we're talking about is it expanding everywhere at the same time in the same way, then yes. The whole universe is expanding. All galaxies are getting further. Well, I say all galaxies, but if something is tightly bound in a galaxy cluster, they're probably not moving away from each other as fast as like different galaxy clusters are moving away from each other. But everything is expanding. Something further from us is moving away from us at a faster rate, just because there's more space between us. So there's more addition to that space over any given time. But yes, the whole universe over space is expanding uniformly. Okay. Do we have...
Sorry.
Oh. No.
Looks like my internet's being unstable at the moment.
Oh. I can go ahead and read through the chat unless you have... I don't know if you see things that I might not be seeing. Okay, while we're waiting, why don't I go on? I'll go on to the next question that I can see. I think Sean's internet is a little off right now. Can you quickly do, from Ed Mizzy, can you quickly do a direct comparison between dark energy and dark matter in a nutshell? So dark energy and dark matter don't have anything in common other than the fact that we can't see them. This boils down to how astronomers name things or how physicists name things. We call them both dark because we can't see. But dark energy is a form of energy. It's something we really don't know anything about other than it's causing the universe to expand, to accelerate. Dark matter, we know, has mass. We know it is matter, it has mass, it has gravity. And we know that even though it's there, like you raise your hands right now, there is dark matter passing through you. We're touching dark matter all around us. But we can't feel it because it doesn't interact with us. It doesn't interact with anything, as far as we know. We're trying to find out. We're trying to find out if we can get it to interact with something. There are a lot of experiments trying to directly detect dark matter. We have not yet, but maybe soon. But yeah, we call it dark because we can't see it, but we know more about it than we know about dark energy. We know it's got gravity, we know it's not going to interact with light, and we can create maps of it. We can, using things like gravitational lensing, we can figure out where it is. Okay, we talked about the rate of the expansion of the universe. I am, by the way, seeing a couple of hands up. I don't know if those are just residual from when we raised our hands for the Big Bang and Big Crunch, or if you have questions. Donna, I think your hand's up and has been up longer. Did you have a question? Or has it...
Yeah, that was from the original part.
Okay. And I think, well, Sean, you're back. So do you want to moderate? I don't know if the other hands up are questions or if we should keep going with the chat.
I could keep going in the chat.
Okay. All right. So yeah, we did talk about the universe expanding at a uniform rate. I've read about missing dark matter in some of the galaxies. Can you explain how it is possible? The universe is a weird place, and for everything that we say, there is always some exception that is doing something weird. It is really weird to think that some galaxies might not have dark matter. Maybe they formed from colliding galaxies, and all their, like, remember, as we said, dark matter isn't interacting, so it just passes through stuff. But perhaps well, these are galaxies, so maybe like the stars just got left behind, or who knows. I think we're figuring it out, but the universe is such a big place that I wouldn't be surprised that I'm not surprised that we have random anomalous things. Fun fact, there are more trees on, so the universe is vast, and so is our Milky Way, but there's sometimes you don't realize how vast things in our own backyard are. There are more trees on Earth than there are stars in the Milky Way galaxy. There are more trees on Earth than there are stars in our galaxy, which I couldn't believe at first. But there are more galaxies in the universe than there are grains of sand on Earth. So, given that vast number of galaxies, the universe is huge and weird things can happen, and we should try to find out how. I imagine if a galaxy is missing its dark matter, it's probably gone through some sort of shock in life. Some, collision with another galaxy or something that probably caused this kind of weird structure. Do we know the percentage of the universe that is dark matter versus not? So that's what we're trying to find out. Currently, what we have is, and I'm going to give you very ballpark numbers because they change each time a new paper comes out. But we have about 3% of regular matter, stuff that we can see. About 20, I said 3%, so about like 25, 26% dark matter. And then the rest, we've got approximately 70% left. Like I said, I'm doing estimates. About 70% is dark energy. And like I said, we have a lot of, this is what we're trying to pinpoint. This is what we're trying to find out. So the numbers fluctuate. The amount of dark energy has been fluctuating between like 69%, 72%. Like, it's been going back and forth for a while, but those are the ballparks.
So I'm back if you need me.
Sorry?
I said I'm back. So the next question that you have is from Donald. It says it's a mystery why we can't in any way sense dark matter in our own Milky Way galaxy. And why doesn't it affect the way stars revolve around the galaxy's center?
I am assuming we're talking about dark matter and not dark energy here. Dark matter is affecting the way stars are moving in our galaxy. Actually, if you measure the arms of the Milky Way, the arms, this is how we found out that dark matter exists. The arms of the Milky Way, at first we thought it was a disk, right? It looks like a disk. Newtonian physics tells us how something should rotate around a disk if the primary force is gravity, right? And the arms of our galaxy are rotating much faster than that. They're rotating the way they would rotate if they were orbiting a sphere of mass instead of a disk. So our galaxy does have a sphere of dark matter around it, which is causing the galactic arms to rotate faster. So it is affecting the Milky Way. Now, if you did mean dark energy, the effects of dark energy are felt on much greater scales. They're felt on expanding the universe, galaxies moving away from galaxies. But the force of gravity within a galaxy is too strong for it to really be affected. Within one galaxy itself, the force of gravity, the the force of gravity is too strong for it to really be affected by dark energy.
So the next question that's here talks about the type 1 supernova. And you had mentioned that the measurements were not where they were expected to be. If we were trying to measure their distances, where were they expected to be?
So it's not the distances that were unexpected. They show up where they show up. It's not like we can expect where a type 1a supernova is going to show up. They show up, but given other factors of the supernova, like what galaxy it's in, we can look at the spectrum of the supernova and see some Doppler shifts in lights. Using other factors, we can figure out how far away it is. So we observe a supernova, we use these other factors to figure out how far away it is, and that then tells us how bright we expect it to look. Because if it's closer to us, we think it's going to look brighter. If it's further away, we think it's going to look dimmer. That expected brightness is what is actually made different because of dark energy. Dark energy interferes in that and then changes the brightness that we see from these supernovae, not their locations.
I do want to be respectful of your time. It's 8 o'clock. Do you have time for a couple more?
More.
Okay. So we'll save the really hard ones now, right?
Sure.
Dan Fox wants to know, should dark matter generate gravitational waves? And has there been any attempt to try to measure that or detect it?
Well, dark matter has gravity, and gravitational waves, for anyone who may not have heard of them, is gravitational waves are how information about gravity is transmitted. Now, the thing with gravitational waves is they're notoriously difficult to measure. We measure spurts of gravitational waves coming from things that are changing very quickly, like what you may have heard of in the news, two neutron stars colliding, orbiting each other and spiraling into a collision. That's something that's changing really, really fast. And so the gravitational waves from that are sort of strong enough that it's easier for us to detect them. And easier is a relative term. It's taken decades, and I don't know how many millions or billions to I honestly, I have no idea how much LIGO has cost, but it has taken ages to try to damp out all noise so we can measure gravitational waves. There is, I know we're looking for gravitational waves that are remnants from the Big Bang. I know we're looking for fainter sources of gravitational waves. The thing with dark matter is it's just sitting there. It's easier for us to measure gravitational waves when something is changing. So there is a gravitational wave observatory planned called LISA, which is going to be in space. And it's a huge project. I know it's expecting to try to see a bunch of things that the normal gravitational wave detectors on Earth can't see. I'm not actually sure if gravitational waves from dark matter is on that list, but you can go look up LISA and find out.
I like this question from Chris J. That says, since we've identified dark matter and dark energy, is there likely to be a dark equivalent of Einstein's E equals mc squared?
Well, that's energy, right? So don't we just say that's dark energy? Am I skirting the question too much? Honestly, this is just scientists being funny about naming things. Like I said, you heard our telescope names; those actually exist. I had a few other examples. I feel like if I ever do stand-up comedy, I'm gonna like have to do a bit on telescopes and how we name them. The Japanese built a really cool detector for their telescope and called it Supreme Cam. Then they built a better one and called it Hyper Supreme Cam. So yeah, the dark is really just us naming something we can't see.
I still want there to be like a dark E equals mc squared, though.
Sure. I mean, well,
It sounds like a good movie.
yeah, I'm sure. we can have science fiction movies with a variety of things that make scientists cringe, but are still fun to watch as movies. Yes. I do see somebody in the chat wanted the music.
Yeah, we've provided that link.
Oh, you got that, the universe
Yeah.
of sound. Okay.
There was another question, and I don't want to put you on the spot, but someone did want to know if you'd be willing to share some of your poetry.
Oh, yeah, actually, sure.
And that will be the last one. That's a good way to go out on.
Okay, yeah, sure. I know Donna actually asked me about this, and I was trying to see if I could work it into the talk, but I was like, okay, there's no time. So if anybody asks, I can. Let's see. Have it somewhere. So I do have poetry that's focused more on the universe and the cosmos, but it's song parodies, and I can't sing, so I'm not gonna sing those now. But if you want, I think there's like a page somewhere. Center for Astrophysics. Where I work right now at the Center for Astrophysics, they did a art and astronomy like internal exhibit. And some of them are there, so I can put this there because I don't want to sing, but then I can share one that's actually a poem. So I'm pretty sure this is sorry, I now have to look for this stuff. Yeah, I think I'm sending you the right page. This will have some poetry, some of mine and other art that other astronomers have done. I can share a poem about gravity, because we've been talking so much about gravity, but gravity a little closer to home. I mean, it's the same gravity that pulls the universe together and also pulls is the same gravity that pulls the universe together and also keeps our solar system going. And this was inspired by a really cool animation of our solar system. We don't actually, or we're not orbiting the sun. Jupiter, Saturn, the other planets are not orbiting the sun. We are actually orbiting the center of mass of our solar system, which is very close to the sun, but isn't the sun, because the other planets have enough mass to throw off that center of mass. And there is a beautiful animation that shows this. System center of gravity. Sorry, I know I'm going off on a tangent, but if I'm gonna read this poem, like this, it has to be accompanied with this animation. Okay. I'm just gonna just watch, like there's nothing to really listen to here. Just look at this. This is Jupiter and Saturn on the outside, and that's the sun. The green star thingy, the green point here is the center of mass of our solar system. And even the sun is orbiting that. So this, whenever, like, I mean, as a physicist, I know this, but seeing it still blows my mind. So, and I'm not gonna let this finish because this is just orbiting. So based on that, I had a prompt from this Cambridge Science Festival thing to do something about action and reaction. Every action has an equal and opposite reaction. So every force comes with its own partner, a simultaneous twin, two forces pulling in opposite directions, two objects, each pushing away, or perhaps drawing the other close. The Earth orbits the sun, as does Jupiter and Neptune and Mercury and merry little not a planet Pluto. We all go round and round, a carousel of rocks and gases held in orbit by our star's inexorable pull. But what a beautiful thought that while the behemoth of fusing gas at the heart of our circumnavigations reigns supreme over our little patch of the Milky Way, watching as we dance to its gravitational tune, we merry little planets pull right back, and the brilliant sun in all its massive glory swings back and forth at the beck and call of our combined little gravities. Yeah, that.
And with that, thank you so much, Ruta. Thank you for joining us tonight. It was great to meet you. It was great to hear you speak. Thank you.
Yeah, thank you for having me. This was a lot of fun. I really enjoyed the questions.
I hope you have a wonderful evening.
Thanks, everyone. Have a great
And
evening.
thank you all for joining us tonight. See you at the next event.